Welcome back to Chemistry Matters, Unit 6, Moles and Stoichiometry. There are many factors that affect the amount of product formed in a chemical reaction that we haven't yet discussed. For example, what if you had a factory that was producing a semiconductor material for use in computers, and you found that changing the amount of reactants, the recipe you were using, also changed the amount of product you were able to make? You'd probably be very interested in determining how to maximize the products you make. And you'd probably also want to maximize your profit. For example, in this problem from the last video in the Unit 6 playlist, we calculated mass of silver, but we didn't mention the other reactant, the silver nitrate, other than saying it was in excess, that was involved in the reaction. Since atoms and molecules must collide in order to react, the amounts of the reactants that we have before a reaction will dictate how much product can be produced. Typically, one of the reactants is completely consumed in a chemical reaction, and once this happens, the reaction comes to an end. Let's head back to our classroom, where our students are getting a chance to see how the amounts of reactants in a chemical reaction can affect the amount of product that can be made.
In this activity, we're going to use the creation of s'mores to explore how the relative amounts of reactants used in a chemical reaction will determine how much product can be formed. So pretend we're starting a company that makes s'mores and sells them for a profit. The ingredients we'll use will be like reactants in a chemical reaction, and the finished product, the s'more, well, it'll be like a product that's made in a chemical reaction. So take a look at the activity sheet I gave you. Each group has also been given a specific amount of graham crackers, marshmallows, and chocolate pieces. Right? So answer the questions as your group proceeds through the activity. And remember, even though the lab materials look delicious, for safety reasons, there's no eating in the lab.
Okay, so the first question asks, what do you need to make a s'more? So we need 2 graham crackers, a piece of chocolate, and 1 marshmallow.
And the second question asks us to write out a reaction for how to make 1 s'more.
All right, we can abbreviate these, so let's write 2GC for graham cracker, and plus 1CH for chocolate, plus 1M for marshmallow, equals 1 s'more.
So now we need to see how many we have of each. So we have 14 graham crackers, 4 pieces of chocolate, and 9 marshmallows.
Okay, let's put these together and see how many s'mores we can make.
Okay, Team 1, looks like you finished making your s'mores. How many were you able to make?
We were able to make 4. We could have made more, but we ran out of chocolate.
We still had 6 graham crackers and 5 marshmallows left.
Very good. Team 2, how many s'mores were you able to create?
Well, we started out with 8 graham crackers, 5 pieces of chocolate, and almost an entire bag of marshmallows.
So we were able to make 4 s'mores.
Yeah, but we ran out of graham crackers. We had 1 piece of chocolate left over and a lot of marshmallows.
Great job, everyone. What you all just demonstrated was the concept of a limiting reactant. A limiting reactant is the reactant in a chemical reaction that limits the amount of product formed. The reaction stops once the limiting reactant is consumed. So if we take a look at the equation for the creation of our s'mores, we can see the proportional relationships between the amounts of reactants and the product in our reaction. So for group 1, you guys ran out of chocolate because you had only 4 pieces. So when you ran out of chocolate, you couldn't make any more s'mores, your product. So if this were a true chemical reaction, we'd say the chocolate was the limiting reactant, because once it was completely consumed, the reaction stopped. Therefore, the chocolate limited the amount of product that could be made. The leftover graham crackers and marshmallows that you had after the reaction are analogous to excess reactants, if this were a reaction. The excess reactant is the reactant in a chemical reaction that remains when a reaction stops once the limiting reactant is completely consumed. The excess reactant remains because there is nothing with which it can react. Group 2, what would you say the limiting reactant was for your experiment?
Well, we ran out of graham crackers, so I would say that was our limiting reactant. Once they were all gone, we weren't able to make any more.
Yeah, and our chocolate and marshmallows were our excess reactants.
Exactly. So chemists sometimes have to determine which reactant is the limiting one in a reaction in order to determine the amount of product that can be formed. This amount of product that can be formed is known as the theoretical yield. Theoretical yield is the amount of product formed from the complete conversion of a limiting reactant in a chemical reaction. When it's unclear to chemists which reactant will run out first, a calculation to determine the limiting reactant and therefore the theoretical yield is required. There are many reactions, however, in which it is very clear which reactant is the limiting one and which reactants are in excess. If we know this information to begin with, then we can calculate theoretical yields based on the amount of the reactant that we are given to begin with in the problem. So let's look at an example together. Ammonia can react with oxygen to produce nitric oxide and water. So let's say that you operate a factory manufacturing nitric oxide for heart medication. Your starting materials are ammonia and oxygen. In your factory, let's assume that it's very important to know exactly how much water will be produced by this reaction, since you're careful to recycle as much water as you can. So given this balanced chemical equation, where 4NH3 plus 5O2 yields 4NO plus 6H2O, when 1.2 moles of ammonia reacts, how many moles of water should be produced? Now, here's a perfect example of a problem in which we know which reactant is going to be limiting from the start. Since the atmosphere contains about 21% oxygen gas, there is more than enough oxygen present for this reaction to go to completion while completely consuming the 1.2 moles of ammonia. So let's do a stoichiometric conversion to solve this problem. Now, the first step would be what, Michelle?
Place what is given to you in the upper left-hand corner of a conversion chart, which would be 1.20 moles of NH3.
Good. And what's next?
We let the units guide the conversion. So we bring down the moles of NH3 down to the next denominator of our chart.
Great. Then what do we do?
Since we have the moles of what was given, we can do the mole ratio step. So we use the coefficients from the balanced equation to convert from moles of NH3 to moles of water. We'd put a 4 in the denominator in front of moles of ammonia, then put 6 moles of water in the numerator.
Yeah, so that allows us to cancel the units of moles of NH3, and we'll be left with moles of water, which is what we want. So let's just multiply 1.2 times 6, and then divide that by 4, and our answer is 1.8.
So 1.8 moles of water is the theoretical yield, and that amount of water can be made from 1.20 moles of ammonia according to that reaction.
Well done, everyone.
That was nice work by our students as they tackled many concepts, such as limiting reactants, excess reactants, and even theoretical yields. This unit also has a closer look video on limiting and excess reactant calculations, as well as several other closer look videos. Another thing our teacher mentioned at the end of the last segment was how the theoretical yield measured the amount of product that could form from the complete conversion of a limiting reactant to products in a chemical reaction. Well, what happens when a chemist performs a reaction and the amount of product that he or she actually recovers is different than what the calculated theoretical yield was? This actually occurs more frequently than you might expect. And chemists are always trying to evaluate their lab technique so that they can run experiments that are more accurate and precise. To that end, one of the most effective ways that a chemist can analyze their recovery data is with a calculation known as percent yield. Percent yield is the ratio of the actual yield and the theoretical yield of a material. Percent yield is a measure of the reaction's efficiency. It's determined by comparing the amount of product that's actually recovered in a lab when the experiment is run, known as the actual yield, to the theoretical yield, which is calculated using stoichiometry. The formula for percent yield is actual yield divided by theoretical yield times 100, which converts it to a percentage. It can be the first indicator of a source of error in the experimental design. Percent yield is always calculated after an experiment is complete because the actual yield from the experiment is required in the calculation. It'll help to walk through an example of a problem in which a percent yield is calculated. Potassium chloride is used to make fertilizer for plants, and it also has medical uses in treating patients with low potassium levels. Let's say you work in a lab manufacturing potassium chloride. When 45.8 grams of potassium carbonate reacts with excess hydrochloric acid, 46.3 grams of potassium chloride are formed. Calculate the theoretical and percent yields of potassium chloride. The first thing we need to do is calculate the theoretical yield of potassium chloride, since we'll need that number to plug into the equation to solve for percent yield. Since the hydrochloric acid is in excess, we can base our calculation off of the other reactant, potassium carbonate, since we know that it's the limiting reactant. So setting up a stoichiometric conversion chart, place 45.8 grams of potassium carbonate in the upper left-hand corner, and then bring down the units to the denominator of the next column. Then use the molar mass of potassium carbonate, which is 138.21 grams, to convert to moles of potassium carbonate. Now, since we've converted to moles of potassium carbonate, we can use the mole ratios from the balanced equation to convert to moles of the desired substance, in this case, potassium chloride. Next, since we need to solve for the theoretical yield of potassium chloride, we would convert from moles of potassium chloride to grams of potassium chloride by bringing down our unit of moles of potassium chloride. Then we can use the molar mass of potassium chloride, 74.55 grams, to convert to grams in this last step. Notice that we're canceling our units, grams of potassium carbonate and moles of potassium carbonate, along the way. We can now multiply 45.8 times 1 times 2 times 74.55, and then divide that by the product of 138.21 times 1 times 1, and we find the theoretical yield of potassium chloride is 49.4 grams when we use 45.8 grams of potassium carbonate. Now that we have the theoretical yield, as well as the actual yield that was given to us in the problem, we can solve for percent yield by simply taking the actual yield, 46.3 grams, and dividing that by the theoretical yield, 49.4 grams, and then multiplying that by 100. We find that the percent yield in this particular problem is 93.7%. The factory was able to produce a very high yield of potassium chloride, almost 100% of the predicted amount. Now that you know about stoichiometric conversion problems and how they can be used, it's time to apply what you've learned in a performance task. You'll be asked to calculate the amounts of reactants and products in rocket fuel combustion. Your teacher will set up a hydrogen gas generator, an oxygen gas generator, and you'll use a common lab pipette to create a small rocket which will fly through the air to hit a target in your classroom. You'll compete with other teams in your class to determine the stoichiometric ratios of the rocket fuel reaction and to identify limiting and excess reactants in the rocket fuel combustion. Your teacher will provide you with instructions from our Chemistry Matters toolkit, and you'll be responsible for carrying out an investigation in which you launch a rocket using a variety of ratios of hydrogen and oxygen propellant to determine which ratio provides the best flight performance to your rocket. So let's go to our classroom where our students are learning how to load their rockets with hydrogen and oxygen propellants.
I've already set up a hydrogen gas generator for you. This bottle contains pieces of zinc metal which react with hydrochloric acid to evolve hydrogen gas. And I've put the formula on the monitor for you. There's a hole in the top of this gas generator, and you can use that to fill your pipette rocket with hydrogen gas. So let me show you how. First, fill your pipette with water. And to ensure it's completely full, flip it upside down, squeeze out all the air you can, a little bit of water, and put it back upside down in there. And now you can see how it's completely full of water. Actually, we have a little bit of air in there, so let's do that again. There we go. Then place your pipette on the gas generator lid like this and let the hydrogen gas fill the pipette as the water drips out into the Petri dish below. Now you can try to ignite the gas using the igniter. So I've attached a wire to the sparker so we can insert a spark into the pipette. So what do you think will happen when we introduce a spark in this pipette completely filled with hydrogen gas?
It might explode.
Wait, if it's completely filled with hydrogen gas, then that means there's no oxygen in there. So I don't think anything will ignite.
Well, let's give the sparker a try.
Right, nothing happened, so that means there's no oxygen in there.
Right, London. Now let's make a prediction about oxygen in the pipette. I've set up an oxygen gas generator here in this bottle. It has hydrogen peroxide diluted with water, and I've also added a catalyst in the form of powdered yeast. The reaction is on the monitor for you. The hydrogen peroxide reacts to decompose into water and oxygen gas. Now the oxygen gas generator has a hole in the lid, so we can fill the pipette rocket with oxygen gas. So let's fill this pipette with oxygen gas and introduce a spark. What do you predict will happen?
I think I'm getting the idea. The oxygen by itself will have nothing to react with. If it's not going to react with itself, the spark won't do anything, right?
I'm not so sure. I mean, I've seen signs warning not to have open flames in areas where there's oxygen gas being used, so there might be a reaction.
Well, let's see what happens. Well, Amaria, you were right to predict that there wouldn't be a reaction in a pure oxygen container. But oxygen mixed with a fuel like hydrogen gas can be a very convincing reaction. So let me show you how to mix hydrogen gas with oxygen gas in your rocket's ignition chamber. We're going to fill the pipette rocket with water, just like we did before. Making sure to get rid of all of the air that's in there. So we're completely filled with water. And then look carefully at the 5 marks on the side of the pipette. You can fill the pipette with a variety of different ratios of oxygen to hydrogen. So let's start by placing the pipette on the oxygen generator, allow the gas to fill the chamber to the first mark, and then we'll pull the pipette from the oxygen generator and place our finger over the opening as we move the pipette to the hydrogen generator and allow the pipette to fill the remaining volume with hydrogen gas. Okay, so let's do that one. Ooh. We'll let it fill up the rest of the way with the hydrogen gas. And once all the water has been removed, we'll remove the pipette immediately. So now we have a pipette with 1 part oxygen gas and 5 parts hydrogen gas. So I'm going to place the pipette rocket on the spark igniter. What do you predict will happen when we pull the trigger?
I bet it'll explode.
Well, let's see what happens.
I definitely heard a popping sound.
Yeah, and there's a bit of fog inside the pipette. Is that condensed water?
Yep, you're right. There's water forming from the reaction between hydrogen and oxygen. So your task now is divided into 3 parts. First, you'll determine the balanced chemical equation for the combustion reaction of hydrogen and oxygen gas. Second, you'll carry out an investigation of every possible ratio of hydrogen and oxygen gas to determine how well each ratio will propel your rocket. You'll use the 5 marks on the pipette rocket to determine these ratios. And lastly, you'll use the results of the rocket test you conduct to determine the correct stoichiometric ratios of hydrogen and oxygen in the balanced rocket fuel combustion reaction. But as always, let's start with a plan. So write out a plan for how you're going to determine the most effective ratio. Let me check your plans, and once they're approved, you can then start your investigation.
As our students begin to plan their Rocket Lab performance tasks, now is a good time for you to do the same thing so that you can perform this lab safely and with accurate results. Once you've got a formal procedure completed, get it approved by your teacher. Then come rejoin me for the next video in the Unit 6 playlist so you can compare your plan to the plan of our students.